Hello, I'm Dr. Sri Banerjee, epidemiologist, biostatistician, public health practitioner. In this brief tutorial, I'm going to talk about how to use SAS effectively in order to conduct a important epidemiological measure, and that is how to determine something called AUROC. A little bit more about what that is later, but first what I want to emphasize is that when you've conducted your epidemiological study, you've completed your design, and then you have your model. How precisely do you determine how effective that model is? What are the types of values that you look at? So area under the curve is one such way that you try to determine what is the effectiveness of a particular model. So just a quick conceptual detour. If we take a look at the receiver operator characteristic curve, if we manually physically draw this out, then you can kind of see the relationship here. So when there is really no ability to discriminate by the model, then the relationship is flat. But then the better the model functions, this is a statistical test or diagnostic test that functions almost perfectly. So the further you go here, then you're actually increasing the numbers of false positives. So somewhere here, you want to design your tests somewhere where the true positives are optimized. So over here, but your false positive rates are not too high. We wanted to take a look at what a typical about the conceptual. You can kind of take a look here and see how this SAS code works, and then compile it. So this is a logistic regression code, which is being run here. But the gist of this is that you can use this to study area under the curve and better understand this. So in the first line here, the SAS help.class, this is actually a sample dataset which is included within SAS Studio. Additionally, what you'll be running here is a historic public health dataset known as the Framingham heart study. And so in the 1940s, about 5,000 individuals were initially assessed for certain risk factors and the relationship with cardiovascular disease. So this cohort, initial cohort, was then followed in subsequent decades to study cardiovascular disease. So here what you'll be comparing is two models. So in these models, the outcome variable is biological sex. And so the predictor variables are height and weight. And so you'll be comparing the model that has been included within the sample SAS help dataset, and then comparing a model, same model that I just described, biological sex versus height and weight, but within the Framingham heart dataset. And then you'll take those two, compare them, and describe which one is the most effective. So do you see how this is taking something that you've learned? You've learned SAS throughout a number of weeks, and then taking that and then applying it to a real life data set, and then providing information. So let's compile this code and see what we get for output. And so it takes a little bit of time, but now you see a couple of parts to this output. So in the top portion, what you see here is kind of a little bit of information about the student data set and then the model. Look at the output further. So the first model, if you remember from the previous portion, was corresponding to the sample data set, the student sample data set, looking at biological sex being predicted by height and weight. So this is the model. This is the significance level for each of the predictor variables, and as it turns out, it's not significant within the sample model. So we would not really expect a too much level of discrimination in this model. So the ability to kind of distinguish between a diseased state or not diseased state, or in this situation, one gender versus another, is that predictive ability is not as much as we would like for it to be. So basically, when you have this direct relationship, as we went and demonstrated at the first part of this, when there's no relationship, it's a flat line. But then when it expands out, then you know that there's some ability to effectively predict whatever the outcome variable is. So let's take a look at the Framingham data set now. And let's look at what that shows. So this is still looking at the initial student data set. And as you can see within the model, the value is 0.7056. So now we're looking at the Framingham heart study, and this was started in Framingham, Massachusetts in the 1950s. So as we would expect, the findings here now, the predictive ability for biological sex is much better from the Framingham heart study. So the value is 0.9185. And as you can see, the curve is really nice. It's bowed outward, which is what we want to see. So this is basically the difference between, so in a continuum, if you were to think about this on one extreme, the diagnostic test being able to perfectly distinguish between your two states. So if it's the disease state versus not disease state, if your diagnostic test perfectly predicts that, then all you have is true positives. But on the other extreme, so think about this as a continuum. So on the other extreme, you have nothing but false positives. So you're not able to predict your outcome variable at all. In other words, if it's predicting a disease state, you're not able to do that, or if it's one gender versus the other. So usually a good test will balance the two. So you can't have one extreme or the other, so you can kind of balance the two. What I'm going to do is I'm going to take a little detour and take another conceptual sort of explanation here and provide this. So let's think about a confusion matrix. Can you think of what a confusion matrix looks like? Before we talk about a confusion matrix, let's think about what creates this confusion matrix. Well, what you will need to think about is a gold standard, and then a diagnostic test, which doesn't quite operate or function as well as the gold standard. So, for instance, if you want to definitively diagnose some sort of internal cancer, a lot of times the initial test is a screening test which has high rates of false positive. So kind of finding the right combination of characteristics for a diagnostic test, that is what we're after here. So a confusion matrix, all it is taking two sort of states. So you have a gold standard, right? I'm going to label that G. And then, so if the gold standard said yes, then you know you have the disease, right? And if the gold standard says no, then you know you don't have it. And then you have some test, usually, which doesn't quite function as optimally as the gold standard. And then this says yes versus no. I'm just going to put Y for yes, and N for no. So what is this here? This would be considered a true negative, because both the gold standard says no, and then the test said no. Now, if both the gold standard and the test agree as a yes, then that would be a true positive. So then, if you have a test that says yes, but the gold standard says no, then that would be a false negative, right? Well, that would be a false positive. So that would be a false positive if the gold standard says no, but the test says yes. And then a false negative, I said, this would be the test says no, but the gold standard says yes. So there you have it. This is a confusion matrix. If you ever get confused, then you can kind of go back to this original 2x2 and then figure it out. So what is this receiver operator characteristic curve telling you? This was actually something that's been in use since the 50s. And that was in radar technologies. And then in medicine, this became in vogue and popular. But in essence, what this is saying is that on the x-axis, 1 minus specificity. So what is the percentage of false positives? So at the outset, you have kind of, here's the start. You have low rates of false positive, and that's what you want in a good diagnostic exam, in a good predictive ability. That's what you want. So you have low false positive here, but here you have actually low percentage true positive. Now that's something you don't want. So let's start changing some of the parameters here, and let's keep the false positives low, but increase the true positive. So here, at some point, we can keep false positives at a minimum, but then increase the predictive value of the model. And this is how this ROC curve works. So the question that you're asking really at the end is that with which model can you increase the true positives, effectively increase this without compromising too many going into false positives. That is your optimal test. And when we look at these two models, the one that came from the sample SAS.help and the Framingham heart study here, then you can clearly see that this Framingham heart study model, which predicts biological sex from height and weight, is optimally is functioning optimally, much more optimally than the other model. So this is in conclusion, this is the power of using this technique to once you've conducted your epidemiological study, to effectively communicate and tell people that this is a powerful model. This is one way to do that. Once everything is said and done, you can kind of see the output data and results, and then you can kind of see the log. So you can then convert this into output data. Once you get to this part, now you're ready to create and generate your PDF output file, which then you can upload and submit when you're ready. So thinking about how to do this, pretty simple. You may not think to do this, but you may see that the download result as a PDF file is not highlighted. So what you'll then need to do is go into print results, and then you can see this other window up here, and then what you will have to do is select save as PDF right here. And for me, this appeared automatically. You might have to actually select the destination and change that. So just something else. And right here you have a lot of important information as to when it was run and the results. Then that lets me know that that this was run separately on a different instance. So these are all the necessary steps in not only once you have generated your model, whether it's through regression analysis or a different technique, but taking that information and really being able to understand and compare models which may not all use the exact same technique, but being able to compare different models. This is the power of the receiver-operator characteristic curve. Thank you for listening.